Great, okay. Our second talk of the session is Timur Tscherbul from University of Nevada, Reno, who will be telling us about magnetic tuning of electric dipolar interactions in an ultracold molecular gas.
All right, thank you, Eric. Thank you, organizers, for inviting me to this wonderful symposium. Okay, I'm not going to pretend this is a full. So this is experimental. I mean, I'm just a theorist, right? So this is experimental collaboration with experimental group of Paul Ketterlich here at the CUA and Professor Alan Jameson at the University of Portugal and his group. So first of all, let me just mention that we think that actually we are responsible in Nevada for half of the discovery of the electron spin, because Sam Goodsmith was a professor at UNR and he retired there, lived there for 2 years, and also the Burning Man festival actually happens near Gerlach, Nevada, and I think this is named after the famous discoverer of the electron spin. Although I think I might make it up, but it is probable. It is probable. So, anyways, this some research direction. I'm a theorist pretty much, but we do all kinds of research related to optical molecules, quantum dynamics, and quantum information science. But today I'm going to talk mostly about this part. And so we heard a lot today about collision complexes and sticking. So this is a picture I stole from this very nice review by this group in this journal. So what happens is basically, there's this lovely collision complexes. The molecules, they stick together, then they, dance in this collision complex, then they dissociate, and they cause trap loss. And that's kind of the picture, right? And so this is all a well-known picture, and it's typically described using the statistical or RKM or /MQDT model that John put forward first, and then it was approved by Tice Commons group. And the idea is basically at short range, as we already heard. There's a forest, and the forest has resonance states in it, and the forest is really dense, right? And then you couple it, you coming in this collision energy, you couple to it, all the hyperfine channels come in a single channel, and then you never come back. So all this flux that comes in here gets sucked in, and then kind of reappears in the exit channel. So the assumption is this resonance force is really absorbing all of the incoming flux. So it's kind of like a sponge, essentially. It's a perfect sponge, perfectly absorbing potential. So, and if you assume that, then you can actually show that with certain other assumptions that RKM is valid, statistical theory prediction of the complex lifetime actually is for KRB plus KRB. It agrees very well with the experiment. So it seems like there's nothing else to worry about, right? So these systems. However, we know that this is not the case. So there's this concept of universality where, like I just mentioned, all the collision flux disappears due to the short-range chemistry, never comes back, right? And so we have to kind of keep them apart using shielding or something. So we're maybe very afraid of this, right? Because once we get in, we never come back, right? So in this, I think my point today, I have several points to prove here in the story. But maybe we shouldn't be that worried about this, because maybe some of the flux will eventually get back, and this is due to non-universal effects, right? So, because like you see, also another motivation to look beyond these universal effects is that you can just, for example, KRB plus KRB reaction rate can be modeled using universal theory, just using two parameters, right? Essentially the mean scattering length, which depends on the C6 coefficient, and the reduced mass. So this reaction rate that actually fits pretty well with the experiment, really totally insensitive to short-range dynamics. So it doesn't really matter what happens. The short-range always gets absorbed. So this is from the chemistry point of view, this is not so interesting, because all the systems will give you the same answer, like this expression. Oh, this is P wave, so this is an extension of this. So basically, from the viewpoint of how can we map out the interaction within the collision complex, this universal is not so promising. So we have to look beyond these effects. We have to actually look at non-universal phenomena to provide insight into short-range quantum dynamics and chemical interactions within the reaction complex, right? So, and furthermore, one example is Feshbach resonances, right? So in the case of Feshbach resonance, it's like a marked non-universal behavior, right? So you have this wild variations of scattering. This is an example for two alkali metal atoms. Of course, this is very common in alkali metal atom world, but has not been observed yet in the molecular world. So the idea is that maybe Feshbach resonances cannot be observed. Maybe they cannot exist in molecular world because of that universal phenomena, right? That has so far been kind of dominated the landscape, right? So, but if we can actually observe the resonance, then we are learning much more about short-range interactions and about control of chemical reactions. So this is an example from a paper that actually erbium collision, it's Lana and John collaborators on. So there's a wonderful experimental observation and theoretical treatment of this enormous number of Feshbach resonances in erbium collision. Just to show you, just two atoms colliding, and you get like 190 resonances between 0 and 70 yards. This is right. Unbelievable. Like when I saw this paper, I was very excited, right? So you can learn a great deal about this, right? However, also in other molecule collisions, like my group has been, involved in this, very, very big, nasty couple channel calculations of this kind of, we try to use realistic interactions that short range describe collision complexes, like using all the channels, right? This calculation has like about like 5,000 channels in it, so it took like many months to complete. But basically, like, we try to use as few approximations as possible, and we see that in other molecule, like Rb plus strontium fluoride, right? So there is a magnetic field variation of inelastic, especially, like inelastic cross-section, right? So, but there aren't many Feshbach resonances. So actually, this is one of the things that puzzles me to this day, why there aren't so few, right? Whereas in erbium 2, where the density of states is much lower, there's so many, right? So that's still kind of like, where are all the resonances? So this is the Li plus calcium hydride. This is like, this calculation, like 7,000 channels. Still, I mean, you put in all this effort and you see one resonance, or maybe two, right? Like, and the magnetic field interval is like in erbium, like you had like 100, like 200, all like up to here, right? So I mean, where are all these resonances? But okay, this question aside, right? So we still don't have the answer, by the way. But there's been some experimental progress really impressive in the group of Wolfgang Ketterle and in the group of Jianwei Pan in China. So atom-molecule collisions have been observed experimentally, and people actually observed Feshbach resonances, non-universal, right? In the non-universal regime. So this is the universal limit, and then you see they observed much higher rate. So that means that some flux actually gets reflected at short range, and not everything gets absorbed, right? Far from it. So we have this markedly non-universal behavior, which actually can tell us a lot about, I think, about this chemical reaction, right? If we can simulate it using coupled channel techniques, for example, right? But so far, this kind of, as far as I know, the origin of this resonance is still up for debate. So whether it's reaction or inelastic scattering, maybe some shape resonance, it's still unclear. So, okay, and here also, 11 resonances were observed by Jianwei Pan group in China between 43 and 200 Gauss. So that's one order of magnitude fewer resonances than in erbium collision. And this system has a huge density of states, right? So that kind of doesn't, again, it goes against all this wisdom. It's included the high density of states, you get, like our KM prediction, it's a longer lifetime, and like more resonances. So what's going on? Again, open questions, so very recent observations. Now, if there is even more, would be even more interesting if someone could observe Feshbach resonances in ultracold molecule collisions, right? Because that would tell us that we can engineer chemical reactivity and maybe create even bigger molecules, polyatomic alkali tetramers from ground state alkali dimers, right? Ideal. And then we can also, hope to use these resonances, if they do exist, for quantum to control interactions between different molecules, right? And so, this paper is the first observation in sodium by Olga's group. So it's very interesting. So there's been quite a few theoretical predictions as to how many resonances there are, and very interesting range of predictions, right? So this is the figure I stole from John's paper. This highly resonant regime at 1 millikelvin is K plus KRB, but there is a lot of resonances, right? So if the resonances get averaged out by thermal, many partial wave regime, right? So they start to overlap, and they start to kind of like negatively, destructively interfere. So you get so-called Ericsson fluctuations, right? So there isn't like pronounced peaks, but there are, kind of peaks, but they're not very sharp. And eventually when you increase your collision energy or you increase your inelastic loss, everything gets like smoothened out, and there's this like background oscillations, right? Okay, so what's going on really? Where are we? So this is like model calculation, model density of state calculation, and we actually, long time ago, we actually did a calculation for oxygen-oxygen collisions, and in the ground state at 1 millikelvin. So this is exact quantum dynamics. It shows a lot of resonances, right? So the predictions are kind of all over the place. From no resonances to a lot of resonances. Okay, and recently, the answer to that question has finally been obtained by Walton's group, and the answer is yes, there is a Feshbach resonance in collisions of two sodium-lithium molecules. So the experiment is, I'm not an experimentalist, so please forgive me if I get the details wrong here, but it's about a few thousand sodium-lithium molecules in a 1D optical trap at about 2 microkelvin, and these are identical fermions in the same internal state. And so a magnetic field was scanned over a wide interval, and only one Feshbach resonance was observed at this magnetic field, which is 335 Gauss with a width of 25 milligauss. So it's pretty narrow resonance, but the magnetic, it's very interesting. So there's only one. The question is what's going on, and why is there only one? So this is like kind of a picture of this resonance. So you see this is background universal loss, and outside of the resonance, pretty much the loss was following universal behavior, universal model. However, near the resonance, it's like up to a factor of 100 above the universal value. So this is like a very pronounced non-universal behavior in collisions of identical fermions. So, okay, so what's going on, right? So if you look at the structure of sodium-lithium, so here's one, like there's a suspect magnetic field, 333 Gauss, where different Zeemanses, so A is the initial state that the molecules were prepared in, they experience a single particle avoided crossing with some of the low field seeking hyperfine states, B1, B2, and B3. So these are the hyperfine quantum numbers. Actually, F is not a very good quantum number in this magnetic field, but M sub F is. So you see that there's a difference between these M sub F values, and so these different spin states. So it must be something related to this single particle avoided crossing. So what's going on here? Well, is it magnetic dipole? First of all, we thought, okay, maybe this is magnetic dipolar interaction, right? Because typically, because there's a barrier, right? So identical fermions, they have this pronounced barrier. So it actually keeps them apart to about 100 nanometers, right? So they cannot get much closer than that, the molecules, so at this temperature of the experiment. So we have to look at the interaction strength at about 100 nanometers. And we need, let me go back a second. So we need a coupling here of about 16 kilohertz to explain the observed loss, the observed universal rate between these channels, A and B1. You may ask why A and B1, not B2 and B3, because B1 has the same hyperfine component as state A, and states B2 and B3, they have different M sub I quantum numbers, so there's no matrix elements of any interaction between A and B2 and B3. So we decided to look at A and B1 crossing. So what happens is that actually the magnetic dipole interaction is a suspect here, because typically these kind of transitions occur outside of the centrifugal barrier, but however, in this case, the delta M sub S values, so that these values these states are not directly coupled by the magnetic dipole interaction because they have this difference in the spin quantum number. So, and magnetic dipole interaction has very strict selection rules. So it cannot couple the states directly, so it has to go through some excited or Zeeman state. And already at 100 nanometers, the coupling is extremely small. It's much smaller than necessary to explain the observed loss. And making it second order to other state doesn't help, right? It doesn't increase it by any stretch of imagination. So, like basically, this is ruled out. So could it be electric dipolar interaction? Well, we have looked at that. So it's much stronger than the magnetic dipole interaction at that 100 nanometer outside P-wave barrier. However, the selection rules are even more unfavorable in this case because they do not couple, this interaction doesn't couple different spin states at all. It's diagonal in both electron spin projection and nuclear spin projection. So in order for this electric dipole to couple these A and B1 states, you have to go through a rotational excited manifold, right? And that is possible. So, but if you divide this coupling by, like the ratio of the coupling divided by the rotational constant, you get much smaller, something much more than 1 hertz. So no, and this is kind of actually, in order to just convince kind of like ourselves, this is the calculation of the coupling matrix elements for sodium lithium molecule of 100 nanometer. And you see no coupling is greater than 1 hertz. And these are typically couplings between different rotational states. So these peaks, they have to be renormalized by the rotational constant. So it actually makes it effectively much smaller than 1 hertz. So we have to, in order to explain the loss then, the only way to go is to postulate the existence of a resonance. So there's this coupling, so there is a P-wave bound state that we denoted here as 3 at short range that is coupled to entrance and exit channel. So this is the hyperfine state A, if you remember from the diagram, and this is the hyperfine state B that become degenerate. So here we assume this energy gap between the states is capital delta, right? So, and that's the setup. So this is this model is actually a model in the limit of large delta is used to describe P-wave Feshbach resonances and ultracold atomic collisions. So Frederick Chevy, I should have, there should be a reference here, 2005. So they proposed the model. So all we did, we took model and generalized it to a very small delta. Actually, it's quite remarkable. In atomic collisions, it's very difficult to get a small delta. So there are pretty much no single particle avoided crossings. So this is very unusual. So we have to actually take this model and generalize it to the limit of very small delta, which it can be done. So state 3 can decay to this entrance channel, to the exit channel too, right? And then it can also decay through chemical reaction because the triplet state sodium lithium molecules, they can actually undergo chemical reactions. So it's not forbidden, right? So there we assume also some decay rate. So we can actually calculate the exact T matrix element by it's like diagrammatic expansion there. You can sum, and then the expression looks like this. So there's a coupling, alpha and alpha prime. So alpha here is 1, alpha prime is 2. Is the coupling in the momentum space between a continuum state 1 and continuum state 2 and the bound state 3. So it's this coupling essentially. So it's wave function of the bound state, G1, times Bessel function essentially, which is the continuum wave function. And these are both P-wave states. So and we assume that the state 3 has the same P-wave character as states 1 and 2. So actually, yeah, so it's this complicated. This is actually integrals of these coupling coefficients. So the bound continuum couplings, right? So this is the amplitude for the transition. So you see there is a couplings in the numerator. There's some factors due to the phase space. There's quantization volume here, and then there's some anisotropy factor due to the fact that it's a P-wave bound state. So it's anisotropic, but oops. Okay. So I decided to, and then there's a password now. All right, so we see here. Right, there's this math that I stopped. Here we go. So this is the amplitude that can be simplified here. So what is important here in this model is the total width of the resonance. So I want you to look at this term that I'm inserting here. So you see the total width of the coupling, right? Because there's a bound state decaying to 3 channels, right? There's 3 contributions. So there's a contribution due to the entrance channel 1, to the exit channel number 2, and also decays due to the chemical reaction gamma D. So actually you can calculate this analytically and show that the coupling due to the entrance channel into the entrance channel of this decay channel of this bound state, it scales like e to the 3 halves, which is actually quite common for P-wave Feshbach resonance, like a O-shaped resonance for that matter. That is actually has to tunnel through the centrifugal barrier. Therefore, the lower the energy, the width goes down. Actually, it vanishes. The state becomes actually very, very close to a true bound state when it gets pushed down from above to the threshold. Now so this is very interesting. This is the contribution due to the decay of that bound state 3 to channel 2, right? So there is very similar expression except there is a delta in there, right? Because there's additional phase space to decay into, right? So generally the decay from 3 to 2 of that bound state to the exit channel is larger. The decay rate is expected to be larger. Although these constants can renormalize the coupling. I mean, there's no reason typically to assume these constants to be different, right? So we expect similar coupling strengths, and this is this reactive decay channel which just stays there, right? Okay, so we have this amplitude, and we have these 3 contributions to the decay width. So now in the experiment, right, we vary the magnetic field. So the magnetic field gets to a point where this delta vanishes. It goes to 0, right? So this is a key mechanism here for the resonance decay. So if we actually calculate the decay rate, which is square T matrix element times the density of states, right? What you get is this expression for the dependence of the decay rate, or the inelastic rate between going from 1 to 2 through channel 3 on the delta tilde is actually just delta plus collision energy, but collision energy is very small, so it's approximately kind of equal to delta. So you see there is this interesting scaling, assuming that there's no chemical reaction decay, that the width of the resonance. Well, actually, here I'm assuming no decay, but here there is a decay. So there is, it doesn't matter. So it's a phenomenological parameter. So there's like gamma 1, and then there is this contribution with this C times delta to the 3 halves. So as we narrow down this gap, delta, so this is very similar to delta tilde, we see that actually the resonance width actually decreases. And this is actually the mechanism we propose for that formation, for the formation of that resonance, right? Because if we plot now this inelastic rate as a function of this delta, the decoupling, the energy gap between the two open channels into which that P wave state decays, we see that there is like a resonance-like feature here. So what happens actually, we are reducing the width of the resonance as we go to the limit of the degenerate channels. We are reducing the phase space available for the decay of that P wave bound state into state 2. So this mechanism is actually uniquely molecular. So maybe there is something like that in atomic physics, but at least I'm not aware of it. Okay. So this is really, you know, maybe where one could find like interesting, like regions of magnetic field to look for interesting Feshbach resonances, where you can have hyperfine degeneracies between different Zeeman states of polar molecules, right? So, and this is just, you know, the argument from the space. It's interesting actually that it can be the case where that, you know, there's a lot of resonances available at any, the density of states is pretty large, so there's a lot of bound states like 3 available at any magnetic field, but because typically delta is large, so this term dominates and we never see them. But as we actually go to this degeneracy, hyperfine degeneracy, the decay rate drops and then the resonance actually appears on top of that universal background. So that's kind of our current theory for the formation of this resonance after we have ruled out everything else pretty much that could be ruled out. Okay, so I guess there is also a model, a very interesting model that was developed in Wolfgang's group. So it actually assumes that the resonance is like a Fabry-Perot, like the bound state is a modeled as a Fabry-Perot cavity, right? So there's a loss rate with gamma 2 to the exit channel number 2. And then there is incoming and outgoing flux, right, due to initial molecules colliding in some initial state. So we can actually calculate the transmission probability, and it actually matches exactly. So if you plot the transmission probability versus gamma 2, which is the decay rate to gamma 2, remember that's proportional to delta, right? So reducing gamma 2 actually causes a resonant feature to appear on top of some background. Right? So it's exactly the same as, roughly speaking, changing this parameter gamma 2 causes, you know, the inelastic rate to increase, right? So due to the interference, actually it's a quantum interference phenomenon, right? So, and again, because this is highly non-universal, actually a value of y parameter was estimated for this system. It was, I think, a little less than 0.04, as far as I remember. So it's really highly non-universal. So it should, in principle, this thing should tell us like volumes about the structure of the sodium lithium bank closure complex. If we could model it, but we cannot, unfortunately, at the moment, do any rigorous calculation because, you know, the system is just too complicated. Okay, so I'd like to acknowledge contributions from Wolfgang's group, and if you're interested, there's this paper on the archive, and perhaps this observation of a single P-wave Feshbach resonance, perhaps it opens up more questions than it answers, because I mean, the question is like, is it really common? Like, this is a molecular feature. If other molecules colliding, like experimentally studied near hyperfine degeneracies, will we see something similar or not? Do we have them in doublet sigma molecules, in laser cooled molecules? Or do they occur in collisions in bosonic? Or is this a fermionic thing? So, lots of interesting questions there, but I'd like to stop here and thank you for your attention.
Question. Go.
So, just a few slides ago, your prediction for this shape of the square, this very pronouncedly asymmetric.
Mm-hmm.
But the experimental data looks like a very symmetric piece. It looked very,
Yes.
it looked like a Lorentzian type shape that I would expect from just the normal inelastic pressure resonance. Whereas this is a very different shape. So how do you...
It's a good question. I think it might be due to the inhomogeneity in magnetic field with the expand, because I think the resonance is extremely narrow. Yeah, the width is extremely narrow. It was about 25 milligauss. So, and yeah, I think it's like maybe there's asymmetry there, but it maybe was not captured by expand.
And just another question. So which side of the crossing of the state is the center of that? Either on the high field side or the low field side? I think one of the early figures. High field side.
Yes, so it's on both.
Well, okay, the sense of that is from high field side, right?
Yeah, so there is a,
So we
Yeah.
can't actually get out in the B1 channel. So at the center of the resonance, there's actually no decay. This B1 channel.
there are other decay mechanisms,
I
right?
know. But
Yeah. So there are the decay with universal law, so not all the flux goes to the resonance. Some of that gets splitted and goes to the
I
universal.
guess the real question I have is,
Yeah.
could this resonance be just due to a bound state below this B1 state? Just a very near threshold bound state?
Yeah, I'm not sure. Maybe, yeah, maybe there is.
That's what I would assume from this picture and this shape of resonance.
Yeah, well, if it's below, yeah, it's a good point. Yeah, but I think currently, like, there's like a magnetic field homogenization experiment that prevent the asymmetry, the direction of asymmetry of the thing. So it's hard to tell exactly whether it's above or below threshold. But I mean, I think the above threshold theory kind of fits.
I think you would see the asymmetry as much as your
Right.
best.
Well, I mean,
This is still symmetric, so it's two orders of magnitude.
but there is also error bars, right?
Yeah.
If you go to this, like, it becomes a symmetric. You can look at it, right?
So in the plot a few slides ago, it looked like you had hundreds maybe of hyperfine degeneracies. Why is this one special? Just
So
one of many.
yeah, it is a good point. I think it's many of those degeneracies have zero. So for example, these ones will not work because their m sub I quantum numbers are different. So the nuclear spin overlap is zero. If you overlap, I mean, no electrostatic or magnetic interaction can couple different nuclear spin states, right? So those are ruled out. So the majority of those crossings have zero hyperfine overlap. So but a few of them have. This is like very large, but yeah. So at others, no observation of resonance was made. So it's kind of like an open question.
So this resonance is so narrow. Could one of the reasons why nobody sees these resonances, could it just be that no one's looking with that stable of a field and scanning?
I think that is very highly probably the case. Yeah. That's. I mean, this was. I think I don't know. Like, you can tell how many magnetic field points were used in the experiment, but
It was scanned by it was like core scan, and it was like in step of 2 gauss, but still I was able to see it. So I think it's doable.
Yeah. It was very fun.
You're an integer.
They got lucky.
If you hit the enhancement value, it's
Near an
yeah.
integer.
Yeah.
Did I understand correctly that your state 3 is a hypothesized state? It's not a state that is known.
Yes, it was hypothesized in order to explain the observation. But I think in any theory you would have to postulate something like this because all the long-range decay mechanisms have been ruled out. So there is no, I mean, how else one would explain it?
Like, is this sensitive to any properties of state 3? Like you mentioned that you assume it's also P-wave. Does it turn out differently if you make different assumptions?
Yes, I think P-wave is yes, S-wave state will decay much faster and might not be, right? So the resonance might not be observable. So just like the case with P-wave resonances in atoms, right? They tend to be quite narrow because of this centrifugal barrier that prevents them from decaying. In addition to some, and also if it's very reactive, you will not see, yeah, because gamma d would dominate everything, and the denominator, at least in this theory, kind of three-state theory, would not depend on anything, on delta, right? Because that would be the dominant constant.
Yeah, is the P-wave state important to be able to change the M quantum number?
Yes, I think so. Also because you're coming in and, well, only for the mechanisms that we were trying to rule out, I would say yes. Because exit channel would have to change M sub L. And therefore, the exit channel centrifugal barrier would be L equal to 3, actually. So it's even higher, yeah, and less probable.
All right, John's giving me the look, so I think I think that's it for a great talk. Timur, come here.